guys, welcome back to another video. Now in this video we're going to be looking at the topic range, which is under again the topic of projectile motion. Now this is the last subtopic we're going to be looking at under the topic of projectile motion. And now this is arguably the simplest or most easy to grasp concept when we are dealing with projectile motion. So guys, after everything we've covered, please, this has to be really easy to grasp. After all, it's going to be utilizing one simple formula or one simple equation, that is S is equal to UT plus half AT squared, but it's going to be simplified to your normal equation, the equation you're used to from early years in high school, which is the speed formula. Speed is close to distance over time. That is the only formula you're going to need in order to grasp the concept of range in projectile motion. So what is range? Now, range in projectile motion, let's picture our parabola over here, which is the trajectory of a projectile that has been launched, say, from this point with a velocity v at an angle of theta. Let's call this point A, and let's call this point the point where it lands B. Now, we have looked at this trajectory before. There's nothing new here. If you haven't seen this before, please watch my previous videos on projectile motion. Now, we want to know exactly what range is. Range is nothing more than the horizontal displacement of the projectile, which has been launched from our point A to a certain point B. That is all there is. What do I mean when I say horizontal displacement? Now, initially, our object is here. This is the point from which it is launched. Now, remember, when it is launched, this is our angle theta, this is our velocity. Now, theta is adjacent to the horizontal, so we know that the horizontal component is v cos theta. The horizontal component of what? The horizontal component of the velocity. So the velocity in the x direction, if you will, if you choose to call it the x direction, the velocity is v cos theta. And then we have the y component. The y component is a velocity of what? Let's call this vy, following the Cartesian coordinate system. Vy is v sine theta. So this is the vertical component of this velocity, and this is the horizontal component of this velocity. Now, what I'm referring to as the horizontal displacement, remember, as our object moves from point A up to point B, at each point in space, the velocity it possesses can be broken down into its component velocities. At each point. At each point during its motion. Okay, sorry about that. Now, so during the motion of the projectile from point A to point B, at each point during its motion, the velocity at each point, at this point the velocity is this, at this point the velocity is obviously this, at this point the velocity is this, at this point the velocity is this, at this point the velocity is this. This being the velocity, it can be broken down into its components, which are this and this. For this we have this and this, for this we have this and this, for this we'll talk about it, for this we have this and this, and for this we have this and this. Now, I want you to recall from our previous examples or our previous discussion on projectile motion. We mentioned that for the horizontal aspect of the motion, unlike the vertical, the horizontal aspect, since the acceleration is always zero, this velocity doesn't change. It's constant from this point up to this point, such that if we want to determine, say, the time the projectile is taken to move from point A to B, given the velocity and the distance, we can simply use the speed formula. Speed is equal to distance over time, where our speed is what? V cos theta. And our distance, say, it's already given, we'll call it d. And then the time we're looking for, so making t the subject of the formula, we have t is equal to d over v cos theta. I'm showing you this simply to illustrate the point that considering the horizontal aspect of the motion, if you do not understand what I mean by horizontal aspect of the motion, please watch my previous videos. Please, you completely benefit. Now, the horizontal aspect of the motion, like I'm saying, has a constant velocity of v cos theta in this case. It might be v sine theta depending on where the angle is situated. Now, in this case, it's v cos theta, but it's always the case, no matter the shape of the trajectory, whether your trajectory is a perfect parabola like this, or whether you have a cliff, and your projectile has been launched from this point and follows this path, which is a semi-parabola, moving from this point A up to this point B, the horizontal velocity will always be the same. The initial velocity here, up to this point here, the horizontal, talking about the horizontal velocity, it will always remain constant, unlike the vertical velocity, which is being affected by gravity, which is being determined by the force of gravity or the acceleration due to gravity. But for the horizontal, no matter the shape, guys, let's say again your projectile has been launched from this point and follows this trajectory. That is, it has been launched with a horizontal velocity of a certain amount, and it follows this path. Again, in this situation, the horizontal velocity remains the same. It doesn't change. In fact, we say this is our V. In this case, the horizontal velocity, since I'm saying the horizontal velocity remains constant, it doesn't change. In this case, if our projectile is launched with a horizontal velocity, the horizontal velocity at each point during the journey or during the motion, the horizontal velocity at each point remains the same. It doesn't change. It's always equal to this. The same applies for this scenario. When our projectile reaches the peak point here, it no longer has a vertical component of the velocity. It's zero now. This velocity, this horizontal component of the velocity, which is still available and which remains available throughout the entire journey, is equal at each point in time. This is equal to this, 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 this is equal to this. But that doesn't apply for the vertical velocity. That is to say, this is not equal to this is not equal to this. It doesn't apply for the vertical velocity. If you want to understand why, please watch my previous videos. I'll continue mentioning that. So, having understood that the horizontal component of the velocity doesn't change throughout the journey of a projectile, when you want to find the range, what did we say the range is, by the way? We said the range is the horizontal displacement from our point A, which the object has been launched from, to the final point, the point to which the projectile ends. In this case, our projectile ends at the point B, so the range is this displacement. This is the range. Now, in this case, where our object has been launched from off the tip of a cliff up to this point, let's say up to this point, the range is this. That's simply the horizontal displacement, guys. Or in this case, we can be a bit reluctant and call it the distance. This is the range in this case. And in this case, where our object has been launched from off the top of a cliff, but first goes up and then down. Guys, it need not to be situated at this point. Our object could be situated again at this point and first go up and then go down. Please do not memorize this. Now, in this case, our range would then be what? Our range would then be from this point, let's use a different color here, from this point, let's call it A, up to this point, B. This would be our range for this scenario. For this scenario, our range would be from this point up to this point. And for this scenario, our range would be from this point up to this point. The range is simply a distance or a displacement, guys. A straight line. And then in this situation where we've got our nice looking parabola, the range is from this point up to this point. That is the horizontal displacement or the distance. Now, how do we calculate the range? In order to calculate the range, we use one simple formula. And our formula, we're already used to this formula, by the way. So I do not expect anyone to cringe when they see the formula. I want to show you the formula. It's simple. I already showed it to you. I'm going to repeat it again. But I also want to show you where it comes from. I'm going to make it real quick. I want the video to be short. Now, this is our initial velocity. Now, the formula is simply speed is equal to distance over time. The d, the distance being the range you are looking for in this scenario. In this scenario, guys, do not call d the range. It's just the range in this scenario. That is, in the scenario where we were playing with projectiles. Now, this is our d, guys. So, if you want to find the range, you simply make d the subject of the formula, and you get speed times time. How do you get the speed? The speed is simply the the speed is simply the horizontal component of the velocity. What would we say that is? That's v cos theta. Vx is equal to v cos theta. Right, so we come here and we write v cos theta multiplied by what? Multiplied by the time. That is the time of flight. The time the projectile took to move from point A up to point B. We looked at this, guys. I'm not repeating the calculations of the time of flight. We looked at this. Watch the previous videos if you didn't see them. We'll multiply by the time of flight. And you get your range. Your range is equal to v cos theta multiplied by time. Again, I'll continue to say this. It might be v sine theta depending on where the angle is situated. If the angle was situated on this point, then we would say v sine theta. But because it's situated at this point, we say v cos theta. The reason being given in the first video I made on projectile motion. Now, this is how we calculate the range. This is basically it. There is no need to explore other methods. This is what you utilize in the test. This is what you utilize in your homework. Where does it come from, though? Real quick, I want to show you where does it come from. It comes from our equation of motion. S is equal to ut plus half at squared. Then, since the velocity doesn't change, the horizontal component of the velocity doesn't change, it means our acceleration is equal to 0. This then makes this entire part of the expression vanish. If we multiply 0, if we multiply this and this part by 0, this vanishes. And we're left with S is equal to u t, s being the displacement, the horizontal displacement in this case, u being the initial velocity. But since the velocity doesn't change, it remains the same. It does not matter. So the initial velocity being what? S is equal to v cos theta. The initial velocity being cos theta. The time, again, the time being the time of flight. This is where the formula comes from. That's it, guys. That's all you have to know when it comes to the range. This is how you calculate the range. What did I say the range is? The range is simply the horizontal displacement of our projectile from the point from which it has been launched up to the point to which it ends, the point at which it finishes its journey. That's it, guys. Thank you, ladies and gentlemen. In the following videos, we're going to be looking at problem sets. We're going to be looking at actual problems related to the range, related to the time of flight, related to peak height, maximum height, and related to velocity. Please stay tuned, don't miss a video. Please leave a like, subscribe, and a comment if you like the video. Thank you, ladies and gentlemen. See you in the next one.